Computers come in various shapes and sizes. The physically distinct units are divided based on the functions they perform and can be related to large systems like mainframes or small ones like the personal computer. Since computers work on data, they need to receive data, process it, and then give back the result in some form of output. These functionally distinct jobs can be used to draw a logical design of the computer parts. A computer can be said to have input devices, output devices, processing unit, and storage devices. The job of input devices is primarily a one-way street. They help to transfer data from the outside world into the computer processor. For example, the keyboard, mouse, light pen, and joystick. Output devices also perform a single direction task of transferring the result of a process from the computer processor to the outside world. For example, the monitor, also called a visual display unit, and the printer. The processor unit is the main computing unit that houses the central processor and primary storage location. It is housed with many other electronic components on a large printed circuit board called a system board or a motherboard. In fact, if you ever opened up the processor unit, the motherboard would be the most visible component due to its sheer size and intricate circuitry. The storage devices allow a two-way communication. They can retrieve data stored on storage media like disks and floppies and send them to the processor. Likewise, they can also receive data from the processor and store it onto the storage media. All communication of the processor unit with the input-output devices and storage devices are done through ports. Just as seaports in a country provide channels for its ships to link with the outside world, here you have understood in simple layman terms the logical design of a computing system and what the functional units are. The more one understands the computer, the better equipped one is to realize the potential of the machine, to recognize the best software and hardware one needs, and to deal with emergencies that may arise while working with it. Whatever data is entered into the computer needs to be stored first before it can be processed. Looking again at the logical design, we see that an important part of the processor unit is the primary storage location. At the outset, let us clarify that the terms storage and memory have come to be used interchangeably. This is because what needs to be stored obviously needs to be retained in memory for future use. Hence, some people call this location the primary memory. The primary storage is also functionally divided into areas. It can be compared to a small locality divided into different plots, each with a distinct address. One address may be the school, another the store, yet another the post office, and several others may be individual residential quarters. Likewise, one area of the primary storage stores the input data. Another area is the program storage area that holds the program instructions that are to be executed. A third area is the working storage space for holding the intermediate result. And finally, the output storage area holds the final processed results. In reality, these functionally distinct storage locations do not have built-in boundaries. This is because they are not physically marked out, but are allocated for the respective functions as and when the storage area is required. So, a specific storage location may hold input in one application and output in the other application. It is like saying the building on plot 1329 in the locality can serve as a church on Sundays, or as a school on weekdays, or as a community meeting hall on every Saturday evening. The inbuilt unique address number assigned to a primary storage location remains the same regardless of its contents. The comparison of the primary storage locations with a locality is similar only to the extent of understanding how different areas can hold different functional items, that each area is identifiable by a distinct address, that this unique address, once assigned, remains the same, irrespective of who lives at the address. But this is where the similarity ends. Firstly, a distinct address in the locality can contain many people or items, whereas one address location in the primary storage can contain only one item. An address location can contain either one data item or one result or one instruction. When a new item is stored in an address location, the previous contents are overwritten. When a computer system requires an item from a storage location, it is merely read and duplicated elsewhere, but not removed. So, retrieving an item from a storage location is non-destructive, while storing an item into a location is destructive. The primary storage location discussed so far is the area that holds the data, instructions, and results while the computer is working with them. This primary storage area is the random access memory, or RAM. The RAM is so named because its locations can be randomly used for any type of storage used by the user program. The RAM, however, is a volatile kind of memory since the contents are retained only till the computer remains on the power supply. The moment the computer is switched off, the contents of the RAM are lost. This can be compared to a calculator that stores the recent calculations only till such time as it is on. The moment you turn the calculator off, the computations and results are lost, and turning it on back again shows the standard initialized display of 0. In the same way, when the computer is switched on again, the RAM locations are initialized to blank entries. When one is talking in terms of the amount of memory one's computer has, one is actually referring to the RAM capacity. There are 65,536 or more such storage locations in the RAM of most personal computers. Thus, in common parlance, a machine with 65,536 storage locations in the RAM is said to have a capacity of 64K RAM. Here K is an abbreviation for kilo and is approximately a little over 1,000 units in computing terms. The relevance of the measurement units for storage is covered later in this chapter. The other part of the primary storage location is occupied by the ROM, or read-only memory area. These locations contain instructions called microprograms that are permanently recorded by the manufacturers. They hold instructions that provide control functions for computer startup and general operating functions. ROM locations will not accept any input data or instructions from computer users. The ROM is a non-volatile memory since its contents are not lost when the computer is powered down. We have discussed so far that the primary location is divided into storage locations identifiable by a unique address. It is generally stated that one address location can contain one data item or one program element. The actual storage capacity of an address in the RAM is built into the computer by the manufacturer. There are several approaches to partitioning the primary storage section into addresses. Approach 1. The primary storage section is designed to store a fixed number of individual locations under unique numbered addresses. These locations are then treated as a single entity identifiable by that address. For example, to store the word pizza, although the individual characters of the word occupy individual memory units, they would be stored under one identifiable address, say 00019. Machines that store a fixed number of characters in each address are called word addressable, and they use the fixed word length storage approach. So, if a word length is say 8 characters long, the address location 00019 would have its entry something like this. Approach 2. The primary storage section can also be organized so that each number address can store a single character. Such machines are said to be character addressable and they use a variable word length storage approach. The variable word length storage approach makes the most effective use of the available storage space since one character can be placed in every storage cell. Character addressable machines hold one alphanumeric character in every address location. Let us take the previous example to store the word pizza. In a character addressable machine, it would require 5 different addressable locations. Here, the word length is 5 characters. In the example of a number, say 125, the word length would be 3 characters. Each of the 3 digits would occupy 3 different address locations. Although the capacity of their storage locations may vary, every computer stores numbers, letters, and other characters in coded form. Computers eventually recognize any item in a coded form. So, in our example of the word pizza, the actual contents in the storage locations would be in a coded machine recognizable form. Computers use the binary number system, represented by 1 and 0, each called a binary digit or a bit for this coding. Each character in the storage location is represented by a string of adjacent zeros and ones which are treated as a unit. This single unit typically consists of a group of 8 bits and is called a byte. Before we go any further, let us appreciate why the binary system was used in computing. The evolution of numbering systems goes back to the time when calculations and computations became a necessity. For arithmetic purposes, positional numbering systems were developed, where the actual number of symbols used in a positional depended on its base. The familiar decimal system of today has a base of 10, meaning it comprises 10 symbols, which are 0 to 9. In any positional numbering system, the highest numerical symbol always has a value of 1 less than the base. Hence, the decimal system's highest value is 9, which is 1 less than the base 10. Likewise, the octal numbering system has a base of 8 and has 8 symbols, 0 to 7. The binary numbering system is no different. It uses a base of 2 and comprises the symbol 0 and 1. Any number in the system can only be denoted in terms of zeros and ones. So now, the question, why was the binary encoding system adopted for computers? It was a mathematical genius named John von Neumann who suggested the use of this numbering system for a number of reasons. One obvious reason why computers were designed to use binary code is that electronic components are two-state devices that naturally operate in a binary mode. A switch is either open, 0 state, or closed, 1 state. A transistor is either not conducting, 0, or conducting, 1. It is not difficult to understand why the relation to the binary system was so evident. Secondly, the computer circuits would only have to handle 2 digits instead of 10. So the costs in building such circuitry would be reduced and reliability greatly increased. Finally, anything that could be done with a base of 10 could also be done in binary. Let us now understand how anything in base 10 can also be handled in base 2. Each position in a number system represents a power of its base, where the power is the position from the decimal point. For example, the positive number 128 in the decimal system can be written in its base terms as the binary number 1101 can be converted into its decimal equivalent as. So binary 1101 is equivalent to decimal 13. We can even convert a decimal number to its binary equivalent. To convert any decimal number into binary, we keep dividing it by the base 2 and setting aside the remainder of each division stage. Finally, when the last division stage results in 0, we extract the remainders of each stage in the reverse order to derive the binary equivalent. Let us take the same number, 13, and see if this conversion process results in 1101. The use of such a small base automatically requires more positions to represent a given value. However, John von Neumann's reasons in favoring the use of binary code far outweigh this aspect. Almost all computers used today are designed to operate using this binary number system. The binary number system you've just learnt about is in its pure form. Computers, however, use a coded version of this system to represent numbers, characters, symbols, and decimal numbers. Although many coding systems have been developed in the last few years, the most popular of them is the binary coded decimal, or BCD. The BCD approach converts each decimal digit into its binary equivalent rather than converting the entire decimal value into a pure binary form. For example, the number 13 would be represented as. The BCD system used 4 bits to represent all decimal digits. This is because the decimal numbers 8 and 9 required 4 positions for the binary equivalent. 4 bits, however, provided only 16 possible characters. This is arrived by the simple computation of 24, being the possibility either of 2 digits, 0 or 1, across 4 positions. Computer designers then used 6 bits and then moved on to 7 and 8 bits to represent characters in alphanumeric versions of BCD. The maximum arrangements possible with the increase in bits was as follows. 6 bits could represent 64 characters, 2 raised to the power of 6. 7 bits could represent 128 characters, 2 raised to the power of 7. 8 bits could represent 256 characters, 2 to the power of 8. Another coding system called the 7-bit ASCII code came to be widely used in data communications network and was the code used to represent data internally in a personal computer. There were also 2 popular 8-bit codes in use, Extended Binary Coded Decimal Interchange Code, or EBCDIC. ASCII 8, which was an 8-bit version of ASCII that is frequently used in large systems. While computers can work very accurately, they are not infallible. If in the course of data input, processing, or output operations, just one bit in a string of 6, 7, or 8 bits got lost, then an incorrect character code was created. This could result from dust particles in the storage media or high humidity levels. To handle this problem, error detecting techniques were developed by computer designers. One such technique employs the method of adding an additional bit, called a parity or check bit, at the end of each 7 or 8-bit code. So, the actual size of the storage location would be 8 or 9 bits. The extra bit was used to ensure that the total number of ones in the code was always even. So, if a character was represented by a binary code in which the number of occurrences of ones was already even, then the check bit would have a 0. If the character represented in binary had an uneven number of ones, then the check bit would hold the value 1 to make the total occurrences of 1 even. In such a technique, if the computer detected an uneven number of ones, it would know that a character code was incorrect. Now that you know how data is stored and represented, you would be in a better position to understand the way measurement units are counted. As mentioned earlier, generally speaking, 8 bits form a unit called byte. From this, we derive the higher units of measurement, starting with the elusive kilo that we mentioned earlier was a little over 1000 bytes. This is derived by the fact that 10-byte locations with a possibility of either of 2 characters, 0 or 1, would be computed as 2 raised to 10, amounting to 1024. 1024 bytes form a unit called kilobyte, or KB, or simply K. 1024 kilobytes form a unit called megabyte, or MB. 1024 megabytes form a unit called gigabyte, or GB. So, the earlier capacity of 64K that we talked about was derived by the division of 65536 bytes by 1024 to get a higher unit of measurement. Now you're in a better position to understand what storage capacities are. when people say that their computer has 128 KB RAM or a 15 GB hard disk. Just as every aspect of computing technology underwent an evolutionary trend for better speed and performance, so did the components that were used for storage. This can be traced by studying the predominant storage component technology in the past. That is, 1940s to 1950s, vacuum tubes were used which allowed only single-bit storage and hence lent to the mammoth size of computers. 1950s to 1960s, rotating drums coated with magnetizable material were used. 1960s to 1975, miniature rings or cores of magnetizable material were used. In all these magnetizable materials, current flowing in one direction produced the 0-bit magnetic state and the current flowing in the opposite direction produced the 1-bit state. The predominant storage component of today was developed in the mid-70s. Most computers since then and even today use semiconductor technology as their primary storage component. Semiconductor technology uses storage cell elements in the form of tiny integrated circuits packaged with support circuits on chips of silicon. There are several semiconductor technologies currently in use, which can really be understood only if one is well conversant in physics. However, here is a simplified explanation. Bipolar semiconductor devices, which are faster and more expensive, are often used in arithmetic logic and certain other sections of the processor. Metal oxide semiconductor chips, which are slower and less expensive, are used in the primary storage sections. The components are referred as RAM chips because any of the locations on the chip can be randomly selected. Here, the part of memory storage being referred to is the RAM. RAM chips also come in two types, dynamic RAMs and static RAMs. Dynamic RAM chips provide volatile storage and require regenerator circuits to keep the contents alive. Are used for random access by user programs, are less expensive. Static RAM chips are also volatile storage devices, but as long as they are supplied with power, they need no special regenerator circuits to retain the stored data. Are used in specialized applications, are more space-consuming and expensive. The predominance of semiconductor chips in modern computers is due to three major reasons: more storage at low cost, compact size, and faster performance. Collaborative efforts on primary storage technology by scientists in US, Japan and Europe have resulted in more compact and faster devices. Using another semiconductor called gallium arsenide or GaAs instead of silicon was a tremendous breakthrough since electronic pulses were seen to move 5 times faster. It used less power, it could operate at higher temperatures than silicon, and it could also emit light. Although we cannot know what technology will dominate in the future, storage devices are predicted to become smaller, faster and cheaper than those in use today. Without going into the technicalities, we have listed some of the technology areas being explored: gallium arsenide, high electron mobility transistors, Josephson junctions, biochips, optical chips, ballistic transistors. Apart from the general purpose storage sections, many computers have specialized storage sections for specific processing and control purposes. One such area is the buffer memory or cache memory. The cache is used as a scratch pad to temporarily store data and instructions that are likely to be retrieved many times during processing. Cache memory units are faster and cost more per character stored than the primary storage. Other specialized storage devices used in computers are for control purposes. These are the read-only memory chips or ROM chips that you are already familiar with. On a recap on ROMs, you will recall that these storage locations store microprogram, the instructions for low-level machine operations. The ROM technology is used not only for machine-related complex functions, but have also found use in the storing of computer games and educational or edutainment material that only need to be read. In the field of specialized storage elements, there are various types of ROM chips. PROM chips, or programmable read-only memory chips. They are used in applications where critical or lengthy calculations are usually carried out slowly by software. The instructions are converted into microprograms and fused into a programmable read-only memory, or PROM. Once instructions are programmed into a PROM, they cannot be altered. EPROM chips, or erasable programmable read-only memory chips, whose contents can be erased by removing them from the processor and exposing them to ultraviolet light rays. They are not used by application programmers because of the method of reprogramming. EEPROM chips, or electrically erasable programmable read-only memory chips. They are like EPROM chips in their purpose. They are reprogrammed electrically by special electrical pulses. Just as there was the need for customized application software, several chip-making firms are now producing customized chips that meet the exact specifications of their clients. The design of custom-made chips had always been a time-consuming and expensive operation that was justified only if there was a large demand for such chips. However, newer computer-based design automation systems have paved the way for customization. Customers are able to precisely select the combinations of storage elements and circuit patterns they need. These are maintained in a library of standard cells or functional circuit blocks. In this process design, cost is low, making it economical to produce customized chips in small quantities. Having learned all about storage components, codes, and capacity, let us now move on to what the computer does with the data. Most of the data entered is to be processed in some meaningful way. The actual processing within the computer is handled by the central processing unit, which comprises the arithmetic and logic unit, also called ALU, and the control unit, also called CU. The most commonly used processors today are manufactured by the companies Intel and AMD. For example, you may have heard of the Intel P3 or the AMD K667. All calculations and comparisons are done in the arithmetic logic unit. Most arithmetic steps use two numbers as input and produce the result as output. Hence, every ALU is designed to manage two data words and the result. It does this by storing the data and intermediate results in special purpose storage locations called registers. These registers are not accessible by users. Apart from arithmetic calculations, the ALU also performs logical operations involving comparisons. Circuits in ALU are generally used to compare two numbers by subtracting one from the other. As stated earlier, a comparison can either result in a perfect match or lesser than or greater than states. These are depicted by the sign and the value of the result. Programs have distinct branch modules provided so that the ALU knows which path to follow based on the result of the comparison. Typically, any single comparison can offer three choices. First choice, if the values are the same when the subtraction results in 0. Second choice, if the first value is greater when the subtraction results in a positive value. Third choice, if the second value is greater than the third when the subtraction results in a negative value. Alphabetic data is also compared in the same way by using an assigned order sequence. The function of the control unit can be compared to that of a manager operations. The CU selects and interprets the program instructions and then ensures that they are executed by the ALU. It is able to provide the requisite data to the ALU by keeping track of the next instruction to be executed and the address of the data items referred to by that instruction. The operations of both the ALU and the control unit are performed at incredibly high speed. These operations are synchronized by an electronic clock residing in a clock generator chip that emits millions of regular spaced electrical pulses every second. The clock uses a quartz crystal, like those found in quartz watches, to provide the timing signal and working pace of the computer processor. Commands are executed and interpreted at proper intervals, and the intervals are timed by a specific number of these pulses. Thus, the speed with which an instruction is executed is directly related to the computer's built-in clock speed, that is, the number of pulses generated each second. The speed of the clock is measured in terms of its frequency. The unit for frequency measurements is megahertz or MHz, where mega means millions and hertz means times per second. Naturally, a PC with higher MHz reading will typically perform faster. Today, PCs at the desktop operate at speeds of as much as over 600 megahertz.